Ancon make. Again, it's not salesy. It's just, you shouldn't feel like it's pushed you too far down that way. But we're going to look at products, obviously. Without talking about Ancon products, I wouldn't have anything to say. So we're going to look at reinforcement continuity systems, starter bar systems and bar couplers, shear transfer mechanisms, basically dowels and shear transfer mechanisms, thermally broken connections and shock connectors, that sort of thing, and punch and shear reinforcement. Those are sort of 4 areas that we're going to look at. It's not all focused on the products, as I say. Start off with bog standard construction joints, because we do this in different types of joints. Construction joints, everybody's poured enough concrete for the day, they've all gone home to watch the telly, they're going to come back the next day and pour some more concrete. What you usually do is if you're casting a slab, or you're casting a column or something like that, and you're going vertically, you just leave some bars sticking out the top of the concrete, you come back the next day, you overlap some more bars, and you pour some more concrete. If you're fixing walls to slabs, or walls to walls, you can't have bars sticking out into fresh air, because what you've got to do is drill loads of holes in the formwork. If you want to attach something to this, you've got to drill lots of holes in the formwork, have bars sticking out, and then thread all the formwork off the bars, and the bars always stick out into places where people want to be working. So other systems have been developed so that you don't have projecting bars from walls. And the most common system that's used is a continuity strip. Ours is called Easy Strip. Everybody does continuity strips. Ours is called Easy Strip with a Z in it. Halfon do one called Quicker Strip with a K and a W at the beginning. So it's like not top end of the market, it's just like cheap and cheerful stuff. An Easy Strip system is starter bars in a box. So rather than having bars projecting out through the formwork, you have a box with a lid on it, you fix that back to the structure, you nail this to the structure, cast your concrete, take the lid off the box and bend the bars out as and when you need them. This has got CARES approval and BBA certification, and it works great for small diameter bars. When bars are 10 and 12 millimetres thick, they're easy to bend into the box, they're easy to bend back out. We use special reinforcing bar so that you don't get any loss of ductility or brittle failure in the bars when you bend them twice. And it's fine for small bars, but big bars, you can't bend them. You can't fit any in the box because the lap length is that you're required to achieve when you bend the bars out is too great. And even if you could, you couldn't bend them. A 20mm bar, you need lots of big blokes with big scaffold poles and big muscles, and at the end of the day they need a big bag to carry the big testicles on it, because everybody's going to give themselves a hernia even on pieces of reinforcing bar. So for larger diameter bars, other systems are used. So this is the way that the Easy Strip works. What we use for larger diameter bars are either starter bar systems or our KSN anchor system. And they're both basically a means of anchoring a casting socket into concrete. So rather than having the bars that you bend out, you actually thread a bar into a casting socket. A starter bar system is basically a reinforcing bar coupler with a bar screwed into the back of it, cast into one concrete element. You cast that in, strike your formwork. The nailing plate there is just to fix the coupler to the shuttering. You strike the formwork where the concrete is being cured, and then simply screw in another bar from that point onwards and take it away from there. And that's fine, except that in a wall, if you're fixing a slab to a wall, as I showed you in the last slide, and this is only, say, 200mm of concrete, by the time you get a coupler in, and the bar is providing the anchorage for the coupler, the bar's going to come out, go straight for 4 diameters, then bend down, and if unless the wall is quite thick, you'll end up with a bar which is either too close to the face of the concrete, or even sticking out the back of the wall. So even better than that type of system, which is available for all bar diameters, is our KSN anchor system, where rather than having a casting socket like that, we have a casting socket that looks like this. So the anchorage is achieved by the flattened end on the forged stud, which anchors it into the concrete there, again to pull out, and the bars are simply screwed into that, and these are installed on a timber carrier. So you push a piece of timber, nail the piece of timber to the formwork with these attached. After the concrete's been struck, you take out the timber and screw the bars into these casting sockets at the bottom of the recess. And what this gives you, as well as a tension and compression capacity, is you get a little key in there to support the weight of the concrete. So the vertical tendency of the concrete to slip down is resisted by this little key arrangement there. So this has big advantages over this. This is a relatively new product. I think we launched it at the concrete show at the NEC the other year. It won best, it's like Crufts, it won best in show or something like that. At a very court, isn't it? But that's KSN Anchor is relatively new. It's kicked off big style in the UK, but because it's a product that we've developed in response to a request from people, not something we've just dreamt up and tried to foist on the market. People have said to us many times, these standard bar systems are great unless you're in a narrow wall and then you just need room to fit them in. With these you can't actually fit it in and it works perfectly well. Couplers, they're both of those sort of couplers of a kind, I suppose, and the starter bar system uses the conventional taper-threaded coupler. Taper-threaded couplers are the industry standard, and they're a means of connecting two reinforcing bars together without having to overlap them. There are various places where you might use that. The starter bar system is one of them, where you thread one bar into the coupler, again a concrete joint, and another bar at the other side. Taper-threaded couplers are the cheapest couplers that we manufacture, the cheapest couplers available really. They have a couple of advantages over parallel threaded couplers in that because the taper-threaded coupler has a thread which gets smaller as it goes in, when you're pushing these bars in and you're winding them in with a torque wrench, you're effectively pushing the bar into a space that's too small for it. And what happens is that this coupler ends up clamping the bar. So not only do you get the full strength load that you require in terms of a pull-out value, but you can also achieve the slip. What we've got to achieve is, when we test these in a machine, which we've got to do after we've developed the coupler, we've got to test it to see that it works. And we've got to put it in a pull testing machine and pull it till the bar pulls out of the coupler. And that hasn't got to happen till we've exceeded the yield strength of the bar by 15%. So we're getting 115% of yield, which we can do with either coupler, but with a parallel, with a taper-threaded coupler, and with all couplers, we've also got to achieve a slip resistance. And under full load, the bar hasn't got to move in the coupler more than 0.1 of a millimetre. It seems ridiculous to me. I mean, it's making reinforced concrete construction into Swiss watch technology, but 0.1 of a millimetre is what the bar is allowed to move, and that's more easily achieved with a taper-threaded coupler because of this clamping action of it. The bar is actually forcing the coupler, and the coupler is clamping the bar. Parallel threaded couplers, because they wouldn't work in the same way, need to have something special about them to make them worth doing. And what we do is, we cold forge the end of the bar before we put the thread on it. Cold forging the end of the bar basically means we hit it with a big hammer. If you've ever hit your thumb with a big hammer, when you've been putting a shelf up a dome, you'll find your thumb will get a lot bigger, and reinforcing bar is no different. So you whack it with a big hammer, the end gets fatter, then you put the thread onto the fat end of the bar, and the thread is actually a bigger diameter than the bar was originally. So this coupling becomes the strongest point along the length of the bar. Rather than the bar pulling out of the coupler in a test, the bar will actually break to one side of the coupler in this sort of test, which meant that traditionally these couplers were used in earthquake zones abroad, where you could not really guarantee what sort of loads you were going to get. You didn't want lots of bars put out of couplers. You'd put these in and you'd know that you were putting no weakness whatsoever into your structure. Nowadays, though, we also do them as a what we call our Bartec Plus system, where rather than cut the thread onto the end of the bar with a cutting machine, we roll the thread onto the end of the bar. And when you've got a rolled thread, you get a much better resistance to fatigue loading, which makes our Bartec Plus coupler suitable for roads and bridges applications where you're getting a cyclic loading. And Bartec Plus actually has Highways Agency approval in the UK, so you can use it in roads and bridges applications. It's one of the very, very few couplers that you're able to do that with. I think the next slide might just show you the cold forging thing. Whacking with a big hammer, put the thread on, and there you end up with an M24 thread on a 20 diameter bar, so you're actually increasing the strength of the bar locally to compensate for the threading. Whatever system you use, you need to put a thread onto the end of the reinforcing bar. And in the old days, we would send out threading machines to everybody who bought any of our couplers, irrespective of the size of the job. So somebody wanting 6 couplers would get 6 couplers in a jiffy bag and a threading machine on the back of a lorry. We don't do that anymore. We keep the threading machines in the rebar yards. So you simply have to order up your reinforcing bar, ready threaded. The engineer will do that anyway. He'll schedule his reinforcing bar with the threads on it, and it will come along already threaded. The threading machine for the taper thread looks like that. The threading machine that upsets the end of the bar and then puts the thread on looks like this. It's a much more expensive piece of kit. As I say, these were very, very rare. There was only one threading machine like this in the UK. We're now taking the threading in-house for our Bartec Plus, so we'll have control of the threading and we'll sell it as an Ancon product. Now, couplers are generally not an economic alternative to overlapping reinforcing bar. Generally, if you just overlap 2 reinforcing bars, it's a more economical way than putting the threads on the end and screwing 2 bars together. But there are instances where coupling reinforcing bar is necessary. You've got to couple 50 diameter bars. The European standard says 40 and 50 millimetre bars have got to be coupled. You can't just overlap them. There really isn't room to overlap them, I suppose. If you've got very dense reinforcement and you overlap all your reinforcement and you double up the area, you can exceed your maximum reinforcement ratio. And when you've got poor quality concrete, what's classed as poor quality concrete, lap lengths have to increase. So sometimes on large diameter bars, a lap length can be 3 metres. And in that instance, so getting rid of a load of bar and substituting a coupler can be an economic advantage. This is an even better example. If you cast in a lift shaft, using couplers, even where it looks like you might not need them, can be very, very cost advantageous. Here we've got small diameter bars, but wide spacings, with a vertical joint. No reason really not to just stick the bars out the top of the concrete, lap some more reinforcing bars onto them. But if you do that, you may need to use an extra pour of concrete, which can be quite expensive. Because if you get your reinforcing bar, which comes in a maximum of 12 metre lengths, and you need to leave a metre of the bar sticking out the top of the concrete to lap your next reinforcing bar onto it, you can only pour 11 metres of concrete in one go. And in a 60 metre lift shaft, that means 5 pours at 11 and another pour at the very top of your building of 5 metres of concrete. If you put a coupler on the end of the reinforcing bar, you can pour 12 metres of concrete in one go, right up to the very, very top of the coupler, screw the next bar in, and you get 5 pours of concrete instead of 6 pours of concrete to create a lift shaft, and saves a lot of time and effort on site, and the couplers more than pay for themselves for that sort of application. One coupler, 2 couplers actually, don't need any threading. I say 2 because the patent on our MBT coupler expired a couple of years ago, and it's been copied now by a company called Lenton, who produce something called Lenton Lock, which is the same thing really. Our MBT coupler doesn't need you to put a thread on the end of the reinforcing bar. It's simply a clamp. You simply clamp the bars in a tube by pushing them down onto these serrated steel saddles in the bottom of the tube. A serrated steel saddle is a strip of steel with teeth machined onto 2 sides. We sit those in the bottom of the coupler, tack weld them into position at each end, and then push the bar down onto them using these pointed, hardened bolts that go through tapped holes in the top of the coupler. And all you do to create a full strength splice between 2 reinforcing bars using this is you push the bars in from the ends, make sure the bar's sitting on the saddles at the bottom, and then start tightening these bolts up. And you don't need to work to a torque or anything, you just keep tightening, keep tightening, keep tightening, and eventually, when you reach a predetermined torque, the bolts will just shear off. And once you've sheared off all the bolts along the length of the coupler, you've got the full strength splice, but you didn't have to put a thread on the end of the reinforcing bar, which is fantastic when you're already at site and the bars are already there and you can't possibly get in and put a thread on. So when you're patching up holes through a building where you've had a tower crane, or you're replacing spalled concrete due to corroded reinforcing bar, you can simply break out a lump of concrete, cut off the corroded reinforcing bar, and rather than have to break out a full lap length at each end to lap a new piece of bar onto, you can break out a very, very short length, half the length of a coupler, slide 2 couplers onto a piece of bar, offer the bar up, slide the couplers over the joint, shear the studs off, job's done. Patching up holes like the tower cranes, if you cut in slabs to put new drains in, you can reinstate the reinforcement using MBT couplers. Any sort of situation like that. If someone has cast a pile cap this much too high, there's only this much bar sticking out the top of the pile cap and you need to lap onto it, you can jackhammer out a load of concrete, or you can drop an MBT coupler on the top and splice it that way. So it's very, very cost effective in those instances. It's not the cheapest coupler in the world, it's not the smallest coupler in the world, but usually it's a good way of putting something right at site that's gone wrong. And it's usually a cheaper way of doing it than the other alternatives. Now when we've got movement joints, and we're rattling through the joints now at a rate of knots, we've got a movement joint in a piece of concrete, which you'll have if your concrete is very, very long. Brickwork needs a movement joint every 12 metres or so, concrete needs a movement joint every 60 metres or so, just to allow the concrete to expand and contract and creep and shrink and move and whatever it does. If you've got a movement joint in a piece of concrete, you're not going to run a reinforcing bar through, because if you run reinforcing bar through, it's not effectively a complete break in the concrete. You need a complete break in the concrete and treat it effectively with separate slabs side by side, which are allowed to expand and contract. Because you've got no reinforcement going through the joint, you'll never want to transfer a moment, a bending moment across the joint. So it'll always be a sort of hinge in your slab. But you might want to transfer some shear from one side to the other, so that 50 elephants standing on this side of the slab, the load from them can be transferred onto the other side of the slab, so you don't get this sort of differential movement. Traditionally, to transfer shear loads across a movement joint, you use a debonded dowel bar. So you put a stop end formwork up on your slab, drill lots of holes through, push a dowel bar through so it's half on each side, debond one side, pretty much like the debonded wall tie. The concrete can then expand and contract, the joint will open and close, and the elephant standing on this side, the load will be transferred to that side through the steel bars. The difficulty with these is that they're a very, very poor way of transferring load from one side to the other. All the weight of this side gets put onto these fingers of steel which press down on the concrete here, get the concrete cracking at relatively low loads. So they're a poor means of transferring load. And you've got to support the dowels. If you don't support the dowels, you'll end up with massive cracks in the concrete caused by the movement joint that you only put in so you wouldn't get the massive crack in the concrete. And the reason for that is that if the dowels aren't supported correctly, as the concrete's placed, they all get knocked about, they point in different directions, the joint is effectively stitched together, then as the concrete tries to move, you get tension cracks generated at the thin points at the end of the dowels, and you get a big crack there. This is Reading water treatment work, so it's a real live job. You just basically have to dig it all out and reinstate the joint again to get this to work. And that's purely because they didn't support the dowels. They just balanced them on a bit of plywood and hoped they wouldn't move about and replace the concrete. Happily, all of those difficulties can be overcome very easily. First thing you need to do is use a dowel with a sleeve. So rather than balancing the dowel across the joint, you fix a sleeve to the formwork on your first concrete element, cast that concrete, straighten the formwork, and then you push the dowel into the sleeve there, and then cast the concrete on the other side. So that ensures that the dowels all point in the right direction, so you don't get the crack as the concrete moves backwards and forwards. And using a plate rather than a round dowel spreads the load over a greater area of concrete and means that you can get more load out of it before the concrete starts to crack underneath the dowel. We can incorporate an edge trim into this. We have a thing called multi-joint where we actually have an edge trim to strengthen the edge of the concrete as well as transfer the shear across. That's used generally in high bay warehouses where you've got lots of heavy plant running about. You've got heavy plant running over here, forklift trucks and things like that, and it'll start to grind off the concrete at the corner, and when fines and aggregates start dropping down into the movement joint doesn't work anymore. So if you can reinforce the edge using the multi-joint system, which incorporates the dowels, you can overcome two potential difficulties with one hit. Now, plate dowels are okay, you get a bit more load out of them. If you want a step change in the sort of load that you can transfer across a movement joint, then you need to look at using a shear connector. Loads of people do shear connectors. We do shear connectors as well, called DSDs. And in an ideal world, that would mean double stainless dowel, because what we've effectively got is two stainless steel dowel bars, one above the other. We link them together over half the length with a web plate and put a couple of crossbars in there so that this part is anchored in the concrete on that side of the joint. I'm sorry, this part, and on that side we have two stainless steel tubes, again with a web plate, we're linking them together and some crossbars, so this is anchored on the concrete on the other side of the joint. You cast the sleeve into one concrete element, push the dowels in, cast the next concrete element, the joint opens and closes as the concrete moves, and this transfers a significantly greater load across the joint than a plate dowel or a round dowel would. 10 standard sizes available. Capacities for the littlest ones, which are generally the ones I carry around with me for seminars. I've got nothing today because I came on Ryanair. You're lucky I'm not studying in my socks and underpants, so I came on Ryanair. Usually I carry the little ones around with me for seminars. They'll carry 2 tons each across a standard 30mm movement joint. The very biggest ones that I don't carry around with me for seminars will carry 95 tons across movement joints up to 60mm wide. And these are the size of the chairs that you sat on. Huge pieces of kit. The little ones aren't so bad to carry around, but the lads in the office would argue that I'm stupid enough even to carry the big ones around, based on the fact that 16 years ago, when I moved from the northeast coast of England, God's country, down to Sheffield to work in the technical department, I maintained a season ticket. We were talking about football earlier. I maintained a season ticket, not at Manchester United, not at Liverpool, at Hartlepool United. So now I live 250 miles from home, and every other week, because I've got a season ticket, I've got to do a 500-mile round trip to see us getting beat 1-0 at home by Burton Albion or some team with no hopers like that. But I'm still not stupid enough to carry these around with me for seminars. The reason that these carry a lot more load than a single dowel is that, bizarrely, what gets a dowel connection failing is the failure of the concrete underneath the dowel, where all the load goes into the concrete. And that That stress in the concrete there is a function of the stiffness of the dowel. The stiffer the dowel, the more load you'll get out of the connection. And you can make the dowel stiffer. I mean, it makes sense. You make the dowel stiffer by making it bigger. So a large diameter bar will carry more load than a small diameter bar. But there comes a point where that runs out of steam. If you actually turn a simple round bar into what is effectively a steel beam, like an RSJ, with two circular flanges and a web, that's about 6 times as stiff as that, and you'll get 6 times the load out of it. We actually reckon that a single DSD 130, which has two 30mm diameter dowels, will carry the same as 6 individual 32mm diameter dowels. So these things can be very, very cost effective, and they're used for high load situations. Situations where traditionally you might drop 2 rows of columns in a movement joint in a structure. You can get rid of a row of columns, cast a sleeve into one drop beam above one column, cast a slab onto the projecting dowels. You've got the movement joint, but you've got rid of a complete row of beams and columns. You can also get rid of the need for horrible corbels. If you're connecting a slab to a wall and you've not got a moment, you're not using the continuity systems that I talked about, usually you'll make a shelf on the wall just to sit the slab onto. But they're horrible to design, horrible to construct. Cast a sleeve into the wall, push 2 dowels in, cast the slab onto that, and you've got the same situation, but much more simple and quick to achieve at site. If you've got movement in 2 directions, which you will get whenever slabs aren't balanced, if you imagine these slabs expanding about the centre line, you'll see, expanding about the centre line, you've got concrete moving in opposite directions over that part of the joint there. So the joint is opening and closing, but you've also got sliding side by side at that point there. And you can accommodate that by having an over-wide sleeve. So you have a sleeve which is wider than the dowel, so the dowel can move sideways as well as in and out of the sleeve. And with the DSD, we weld the circular sleeve in the centre of a box. Just a little tack weld each end. The dowels go in centrally, and then the forces in that direction break the little tack welds and allow the dowels to move sideways within the box as well as in and out. DSD-Q, by the way, lets you know that that doesn't mean double stainless dowel, because nobody would work out what the Q stood for. It's actually something in German, this. It's a Swiss invention. You've probably been sat there, right, thinking, this bloke's really boring. How can I pass the time? I know what I'll do. I'll see how many Swiss inventions I can think of. And I bet you came up with the cuckoo clock and the Toblerone. Well, next boring CPD seminar, you've got another one, the DSD. This is invented by an engineer in Switzerland who has the perfect engineering job. He sails on Lake Lucerne all summer in his little yacht. He skis at Davos all winter and rings us up once a month and asks us how many of these we've sold. Because every time we sell one, he gets a couple of bob. So all you need to do is dream up something like this, get on Dragon's Den, and you're made for the rest of your life.
How long have those ones been around?
Ages. In fact, I was recruited 23 years ago specifically to sell DSD sheet.
We spent months doing a composting plant scheme trying to solve that problem.
Honestly? Should have got me in a few months ago. You'll know next time. Occasionally, the movement joint is only required temporarily. That's generally, as you may be aware, on post-tension slab, post-tension buildings, where you need a movement joint, not necessarily because you've got vast amounts of concrete, but because you've got to take up initial shrinkage of the concrete. Post-tension slabs shrink dramatically over the first few weeks, and you need to accommodate the movement, the shrinkage. What's generally done is you leave a strip of concrete unpoured, with bars overlapping within that pour. The joint opens as the concrete shrinks, and then you come back afterwards and fill in this in situ with concrete at some later stage. Nightmare. Much better to use a dowel bar like that, which will allow the concrete to, the joint to open up, and then we'll lock the whole thing together with a high strength resin afterwards. What we have here is a single round dowel anchoring the concrete on one side with a nut and washer. On the other end of this dowel, we've got grooves machined into it, and we have, in the DSD-Q type sleeve there, we have a funnel that comes up at the top. When all the concrete is shrunk and this joint is opened up, we simply drop a plate with a notch in it into the top of the sleeve there. That nestles onto the grooves on the dowel bar. Then we fill the whole thing up with concrete. The joint is then effectively locked together, and you can transfer 100 kilonewtons of tension through the dowel bars as well as the shear, so that you can actually anchor all your floor slabs into the hard points of the stair towers and the shear walls and things, so that your building is resisting sway, so your building doesn't actually fall over. Obviously, you can do that where you're expecting some bending in the slab. You can't do it this way you're expecting bending. This won't resist bending, it will only transfer shear. So rather than being put in the middle of a slab, it's generally put in hard up against the point where you're attaching your slab to your shear wall or to your concrete stair tower or lift shaft or whatever. And we do that generally using the KSN anchor. So we've got the KSN anchor that we talked about earlier there. This is a large diameter thread that's stood with an internal thread, and we simply screw a dowel bar into there. After the initial shrinkage has taken place, drop the plate in, pour in the stuff into the top, and then your slabs are still anchored to your stair towers and lift shafts. The first time this came up for me was in Dublin, actually. We worked with White Young Green, who were down in Dunleary. I think they might not be now. I used to work for White Young Green a lot of years ago. We were a third division outfit, I always thought they were a bit like my football team. I got called across to White Young Green for the Smithfield development, which you're probably familiar with, somewhere in Dublin. And we for weeks and weeks, we designed in DSD shear connectors. And at the very last minute, the lads from White Young Green said, so how do these things take the tension across the joint? I says, you can't have tension across a movement joint. The idea is the movement joint opens and closes and up. You can't transfer tension. It's not a movement joint anymore. And what they really wanted, but what we didn't know, was they wanted this. They wanted temporary movement and then to be able to lock it up. So I don't know what was done in the end on that job, but this is what they really needed. But unfortunately, it was before the days when we actually had this thing. If you've got a thermal break in your concrete, you're probably connecting a balcony to a floor slab. If you're connecting a balcony to a concrete balcony to a concrete floor slab, you can't just run the floor slab out through the building envelope, because you get a massive cold bridge which keeps the architect awake of an evening. And I think it's our duty as engineers and people working for contractors and things to keep architects happy. That's the main purpose of my life, is to keep architects happy. So what you do is, when you've got a concrete balcony attached to a concrete floor slab, you incorporate a block of thermal insulation, so you've not got a massive cold bridge. The most common way to do it is to use a shock type, Halfon type, Ancon type balcony connector, which is a block of rock wool insulation encased in a sort of skeleton of steel because it's very unrigid, and it has bars going through it to connect one side to the other. Bars going through the top, you get three mechanisms. When you're connecting a balcony to a floor slab, there are three things that can happen. The balcony can slide, well, two things that can happen. The balcony can slide vertically straight down the side of the building, or it can simply tip over like that. So you've got to be able to resist these two methods of failure. What we have is bars through the top, which pull the balcony back up the top, and compression studs at the bottom, which push the bottom of the balcony out. So to stop it doing that, you push and pull to keep it level. And then we have bars which come through the top, slope down and come out the bottom, and they effectively act as a bit of rope, pulling the balcony back up to stop the balcony from sliding down. These are very, very thermally efficient. They're usually 80mm thick. They're fire protected. They've got sound property insulation, but they're horribly expensive, generally speaking. So as well as doing the high spec type of system, we also have a more cheap and cheerful variation where we replace the rock wool with CFC rigid polystyrene, the sort of thing that you get your fridge or your TV delivered in, but much denser and more solid. We still maintain the stainless steel bars going through the top to stop the balcony slide down, because they go through an open joint. But rather than having stainless steel bars through the top and a compression stud at the bottom, we just run a tube through the polystyrene. And by running the tube through the polystyrene, we can simply run a carbon steel bar straight through from one side to the other. So you're using bog standard normal reinforcement. It gets it much cheaper, and you can use this. All you need to do is make sure that when it's installed, they put some bars through the tubes. We have had one instance where they decided not to do that, and luckily we spotted it before the balcony was built. But with a shock type connector or our Isotech connector, it's all integral and the bars are there. With this, you do have to put some bars through these tubes as a sort of... But the idea is that any moisture that's slopping about on the top of the slab can get onto this bar and cause it to corrode. So we make this in stainless steel. It's effectively pulling the balcony back up. The bars that go through the top and bottom there are completely isolated from any moisture by virtue of the fact that the tubes projecting the concrete fill up with fines and block up, so you can use bog standard carbon steel reinforcement and make the whole thing a lot cheaper. You can also get rid of a bar at the top. If the balcony isn't cantilevered, it doesn't need a pull there and a push there. If it's sitting on a wall at the front, you can get rid of the bar going through the top and just have the bar through the bottom, just to equalise the sloping load in that. So that's another advantage. And you can miss out the odd bar. If you've got a down pipe coming through your balcony or a drain, On the other type of system, you can cut bars off but to go around a downpipe, but you don't know what effect it's having. With this, you can miss a bar out, and you can compensate by making the other bars bigger diameter so they're a little bit stronger. So there are various advantages in this. When I say it's more cost effective, I did a combined CPD seminar in Poole, in Dorset, to a weird consultant engineers called Calcinotto, they were called. And this Julian Calcinotto was about 14, and he set up this business, and he was obviously a multi-millionaire. And he sat in the CPD seminar with his right-hand man. And when I came out of this, he says, "Oh, you're saying these are cheap?" He says, "But I bet you still charge £15 a metre for them." And he's the lad who was sat next to him there, his second in the says, "It won't be £15 a metre, it's a bit of polystyrene, it's going to be coppers." I said, "I'll find out for you." So when I came out of CPD, I rang our office and I said, "Can you give me a price for a typical 200mm piece of Isolan thermal brake with the reinforcing bars in and a bit of stainless steel rebar?" And they said, £60 a metre. So I had to go back and say, "You were right, it's not £15 a metre, it's £60 a metre, but the shock equivalent is £130 a metre." So relatively speaking, it's still quite a cheap item. I think these things are just an expensive thing to produce in any case. I don't usually talk about price, and Dan will probably give me a Chinese bell on the way home for get straight out of my area of knowledge. And lastly, the very last thing I want to talk to you about, because you've all been very, very patient, is reinforcing against punching shear. Again, we're talking potentially about post-tension slabs. We're certainly talking about flat slabs. And when you've got flat, thin slabs attached to small columns at relatively wide centres, you can get a potential known as punching shear failure, which is basically the bed of nails principle. If you blow up an airbed or a lilo or whatever you call it over here, we call it a lilo in the northeast, the thing you swim around in on the beach. Blow up one of those, lay it onto a bed of nails, and then lay on it, all the nails will pop through the plastic. It's exactly the same if you've got a thin slab equivalent to a piece of plastic, and small columns equivalent to nails, they will pop through the slab. It's basically because the slab is too thin, or it's not reinforced sufficiently, or the loads are too high to transfer the shear from the slab into the column. So you get this, well, you get the column pushes through the slab. Traditionally, to reinforce against that, you put links in. You put links between the top and bottom mats of reinforcement to stitch across this crack plane, and you space these out at the centres designated by the standard. To some extent, links like that have been replaced by stud rail systems, where rather than links you have a stud with a fattened end, each end at least 3 times the diameter of the stud, and these are simply spaced out on rails. They're designed in by computer program, by the architects and the engineers, or by us, by lads in our office who sit there all day designing these things. And the advantage for your guys is that they're available in lots of different sizes, and they come just as a ladder, and they're simply dropped into the reinforcement case. So rather than having to make links around the top and bottom reinforcement, which might be quite sparse, if it's a post-tension slab, there's likely to be very little reinforcement top and bottom, but rather than having to make links which are wrapped down, simply come along like this, drop these things in around the head of the column, and they're very, very easy, quick to install, and easy and quick for the engineer to inspect and make sure that they've gone in correctly. You can fix them bottom up. The rail, as you'll see, has a gap in the middle, so you can put nails down into the structure, but generally they're simply dropped into the top mat of reinforcement to save money in that way. As I said, they're designed in on a piece of software, which I'm not going to demonstrate, because if you demonstrate software, you need to be good at it. Right? These lads who come in our office, and they're fantastic. Look really slick. I'm rubbish at something. I'll be pressing Control-Alt-Delete and having to ring our IT department and things like that. So I'm not going to try and demonstrate it. But you put in, or the engineer puts in, all the things he would put in if he was designing the shear reinforcement by hand, and he gets a little drawing that you can drop onto a reinforcement drawing and send to you guys. If you've got links and you want us to convert them to these to get a price comparison, we can do that. If you send us in a drawing with all your links shown on it, we can sort of transpose it to our punch and shear reinforcement and do that for you. Lastly, because I'm sure you guys are people who ask, we have what we call a new product development team. We all sit there on 60 grand a year, twiddling their thumbs and looking out the window and things like that, and coming up with new products, like the ones like the lockable dowel that I mentioned, things like that. Trouble is, a lot of the new products that come up with are rubbish, right? Because they dream them up, think, oh, everybody will want this, and we send it out to market, and everybody says, we don't want that, that's really rubbish. So if your feedback is something that can be really helpful to us and will get me 20 quid. If I go in with a new product and say, let's develop this as a new product and it gets considered, I get 20 quid right now. And I don't mind splitting it with you. So if you're sitting there every day reinventing the wheel and designing something and thinking, or sorting out some detail and thinking, I wish someone would invent something that does this so I don't have to do it over and over and over again, then you need to tell us, and maybe we can come up with something which will get things moving along more readily inside and get me and you 10 quid each. That's about 12 euros, that's worth having. So that's all I've got to say, except that everything I've talked about is on our fantastic website, www.ancon.co.uk. I was in London the other month and an architect said to me, that's my favourite website, and I thought, you haven't seen many websites, have you? That's your favourite website. So that's all I've got to say. That was your chance to chip in with any questions you didn't chip in with. But as I said, don't feel obliged to chip in with questions. You know, people think, oh, we've dragged this lad from Mars, we better show we're really interested and ask him loads of awkward questions. Don't think that. Think he's probably going to go for a pint now. We might as well just let him go and have a pint. But thanks, guys. Anyway, I hope that's been useful for you. And I hope you'll find lots of opportunity to buy lots of our kit from these guys in the back there. So thanks, thank you.
Thank you.
Why not stamp the different grades of wall ties? So the very first anecdote about them all going into
With a stainless steel?
Yeah. That's all.
Well, probably the reason is that it would only be necessary like one job in 100 and nobody would pay for it. Anything that costs more money. Like Carillion used to say to us, because the standard wall ties suit various cavities, but what happens is they get built into the inner leaf first. So they're not laid onto two beds. So they get built in the inner leaf. And sometimes they don't have enough embedment in the outer leaf after that. And the Carillion brickboard said, can you put marks on the wall ties that says, you know, embed it here if it's this cavity? And we looked at it, and it was going to cost, 10 pence a wall tie, which trebles the price of the wall tie, and just nobody buys it anymore. So we just says, no, your brickies are going to have to do their job properly and work it out. So that's it. So it's all cost. That's what it all boils down to all the time. That's you lads, people who don't want to pay more money.
Your starter bars and that, they're all CARES approved.
They are, yes. The starter bars are CARES approved. The new Bartek coupler is CARES approved. The MBT coupler is BBA certified, it's not CARES approved. And the KS anchor, is a KS anchor CARES approved? I don't think it is it yet? No.
But when you sell to a non-CARES approved company,
Yeah.
CARES doesn't really follow through.
Well, it's probably, most of the companies we sell to probably have non-CARES approved, so maybe we just don't need to bother.
No, but like, I mean, if I buy a sheet of mesh from CRC McMahon, who are CARES approved,
Yeah.
it's CARES approved. But if they sell it to builders providers, and I buy that same sheet of mesh, it's not CARES approved.
Is that right?
Or SIG CARES approved or Longs.
So, like say, Long Construction or any of these distributors are not CARES approved.
Because CARES follows the product, not that.
Yeah,
No,
I thought CARES was
no,
Neil not straighten that out.
I don't think it does. No, I'm still not. CARES CARES will say that it doesn't follow through.
Yeah.
Chain of custody.
Chain of custody.
But what could these lads do to it to make it un-CARES approved?
Well, CARES would say that they should be CARES approved.
Oh, right, yeah. That's I'm winning it.
It's chain of custody.
I'm sure. I'll look at that.
Well, Neil is up there already.
What we have to do then is, we have to sell these lads direct and just give you some money.
No, that's okay. That would be the easiest way.
I don't mean very happy. They might trust us for the first week or two.
Well, they buy enough off us, I don't mind, you know what I mean?
I didn't mean you personally, somebody. I meant SIG.
All right.
I'm not building up your retirement. Right, guys. Well, thank you very much.
Thank you.
Thank you.